Good morning, guys. So in this solving session, we're going to solve about the instantaneous center of zero velocity for a rigid body, as well as the acceleration. Are you seeing the screen and hearing me, guys? Okay. So let's start. So as we said, guys, in the video lecture, the instantaneous center of zero velocity, if located, could make our life much easier, because in fact, if I know where is this instantaneous center at this instant, and don't forget, guys, that this IC could be variable for each instant, and that's why it's called instantaneous center of zero velocity. Now, if I know where is this IC, I can find V. I can find the velocity for any point on this body by simply doing omega times r, or the angular velocity times the position from this point considered to this IC. Right, guys, and as we said in the video lecture, there could be a lot of cases. For example, if I know the velocity at A in vector form, which means I know its magnitude and its position, I can find, and its direction, I can find the position of IC, and then from the direction of rotation, I can find where it should be located, at the left, at the right, upward, downward. But I can find its position in magnitude, and then from the rotation, I can find its real position. And then if I have two velocities, I can do the intersection between the lines joining, for example, the perpendicular line to VA from A and the perpendicular line to VB from B. And then if there is an intersection, then this will be the instantaneous center of zero velocity. And don't forget, guys, that if there is no intersection, which means if the perpendicular line to VA is parallel to the perpendicular line to VB, no intersection, this means that no instantaneous center at this instant. There is no instantaneous center of zero velocity, which means at this instant omega is equal to 0. The angular velocity at this instant is equal to 0, and this means that at this instant there is no rotation, there is only translation. VA will be equal to VB, but this doesn't mean, guys, that there is no alpha, or there is no tangential acceleration. There's gonna be a tangential acceleration, but the normal acceleration will be equal to 0, since omega will be equal to 0 only at this instant. So remember, guys, from the general plane motion, if V is equal to 0, this doesn't mean that A is equal to 0. V could be equal to 0 at this instant, but I can have an acceleration. So don't be confused with this fact. Now, if I have two parallel velocity, however, their points, their starting points A and B lines on the same perpendicular line to VA and VB, the instantaneous center of zero velocity will be the intersection of the line of two lines. The first line is the line joining their ends, and the second line is the line joining their starting point, right? And whenever I know V, whenever I know IC, I can locate IC, I can find V as omega times R. But whenever A is a fixed point, so VA is equal to 0, yes, but if A is a fixed point, so guys, if A is a fixed point, which means it's a pin, then VA is equal to 0. A is considered an instantaneous center of zero velocity. In fact, A would be considered the center of rotation always. It's not only this instant, at this instant. If A is fixed, A will be always the center of the rotation for being, let's say, AB, all right? But if A, for example, is a common point between a fixed object, a fixed body, and another beam, then A is also considered a center of rotation at this instant, right? Because VA will be also equal to 0, which means, guys, if I have a pin, then VA is equal to 0 for any instant. A is the center of rotation. If not, but if I can locate IC, and let's say IC is A, then A at this instant has a 0 velocity, and I can consider A at this instant the instantaneous center of 0 velocity. All right, guys? Now, let's start by example line. My advice for you guys is if we have to apply the instantaneous center of zero velocity, is to indicate the velocity's direction. If we know them, like in this example, I know that A is restricted in this slot as well as B. Then I can find the direction of VA and VB. VA will be horizontal, VB will be vertical, which means from this fact, I can know where is the instantaneous center of zero velocity. So my first advice is to indicate the known direction of velocities. And my second advice is to indicate where do I have a zero velocity. So if I have a pin, for example, or if I have a common point between a fixed body and a moving body, so where do I have a zero velocity? All right? So guys, here I have a square plate that is confined within the slots at A and B, and this square plate is rotating, all right? So it's rotating with theta is equal to 30 degrees. Now what you have to know, guys, that if this square plate, this is one body, so if it is rotating with omega, then each segment of the square plate will be rotated with the same omega because they are all belonging to the square plate. All right. So if I know omega for one of these segments, then omega will be the same for the whole square plate, for the whole segments. All right, guys? Now, what do I know? I know that when theta is equal to 30, point A is moving with the horizontal direction, of course, because it's confined within the slot at A. Point A is moving with VA is equal to 8 meters per second, right? So as I said, my first two advices for you is to find the known direction or to find the zero velocity. Now here I know the direction of VA and I know the direction of VB. Since VA is moving in this direction, then this means that this square plate is moving counterclockwise, and this means that VB is moving downward. All right, so this is VA and this is VB. Now, since I know their direction, I can plot their intersection, and this will be what? The intersection of their perpendicular lines, and this will be the instantaneous center of zero velocity. So this should be vertical. All right. And I'm going to rotate it. And this is the perpendicular line to VB. Now the intersection will be what? The intersection will be what, guys? This intersection will be what? The intersection of these two perpendicular lines to the velocities at A and B respectively. This will be what? IC, the instantaneous center of zero velocity for the whole square plate. Why is it for the whole square plate and not for AB only? Because AB belongs to the square plate, which means this square plate has the same omega for all its segments, which means it has the same IC. So I know the instantaneous center now of zero velocity for this square plate, all right? Now, can I find the distance ICA? Yes, I can find this distance because, in fact, if this is 30 degrees, then this is also 30 degrees. And since I know AB is equal to 0.3, then I can find ICA, right? So what will be ICA? ICA will be cosine 30 times 0.3. So ICA will be cosine 30 times 0.3. And this means, guys, that VA, which is known, VA is known, right, will be equal to omega times ICA. ICA is known, VE is known, then I can find omega. And this means that omega is equal to 8 over ICA. And then this means that omega will be equal to 30.79. So I know, guys, now the angular velocity of the square plate. All right, so it has an angular velocity of 30.79 radians per second. Now the question is to determine the velocity at point D. So in order to do this, guys, I'm gonna find the velocity of point B and then relate D to B. Okay, so what is the velocity at point B, for example? The velocity of point B will be this distance In fact, there's no need to find even VB because the question is to find VD. But I can find ICB. What is ICB? Because I'm going to use it later on to find VD. ICB is, of course, sine 30 times 0.3, and this means that this is 0.15. Okay? I know now, guys, omega of the square plate. So if I know D, IC, I can directly find VD. What is VD? VD is equal to this omega that I know times what? Times ICD. So what is ICD? How can I find ICD? In fact, how can I find, guys, ICD? In fact, what are the inputs that I have? I know that BD is 0.3 in the triangle BICD, and I know that BIC is 0.15. And I can also say that this angle right here is equal to this angle right here, all right? Because AC and BD are parallel, so it's also 30 degrees. So, guys, what theory should I apply in order to find ICD? How can I find ICD, guys? Cosine law, perfect, Batul, yes. So guys, you have to put on your mind that if I want to apply the relative velocity equation, which is a vector equation, I don't need the cosine and sine laws because in fact the direction will be given and any inputs will be given in I and j. Now, if I need to apply the knowledge for the instantaneous center of zero velocity, you have to know that I need that trigonometry and I need the cosine and sine rule. All right, like this case, how to find ICD, which is a segment of ICDB triangle. Here, I have to apply the cosine rule because I know these two segments and I know the angle between them. All right? So ICD is equal to radical BD squared plus BIC squared minus 2, the product of these two segments cosine the angle between them. Cosine 30. So this is ICD. All right. So if you do the calculation, you're going to find that ICD is equal to 0.185. Then whenever you know ICD, you can find VD. So what is VD? In fact, VD is equal to omega times ICD, which means it will be equal to 5.72 meters per second.